One second. Right. So for 1 mark only, they ask you the field strength. So it's best to write that it is the force acting per unit charge. It's even better if you add positive charge, but it's all right, even if you write it like this. Even uh, my voice is an issue. All right, so it gets. Is it okay now? Okay. All right. Let's see. Okay, so I was basically talking about the this question. So okay, so we can use E equal to V over D, but then we don't have voltage. So I think the best way would be that if I could use KQ over R squared, and I want to find what is the charge when the electric field strength will be 2.0 times 10 raised to 4, and you can multiply it with the radius, which is 26 centimeter, and I can write it as 0.26 whole squared, and then divide it by 8.99 times 10 raised to 9, and probably I'm going to find Q. So let's try this one out. 2 into 10 raised to 4 multiplied by 0.26 whole square. And then you can basically divide it by 8.99 times 10 raised to power 9. So this is how I think the maximum charge should be 1.5 into 10 raised to power minus 7 coulombs. All right, kids. Then in the next one, it says an isolated mid-sphere B, also with charge plus Q, has a radius of 52. Calculate the additional charge in terms of Q that may be stored on the sphere before the electrical breakdown. Okay, right, I understand that. Now, as you can see from the formula, times R squared equals KQ. Now, what I do, whenever you have to compare like things with some values common, like electric field strength or the maximum electric field strength is common, K is a common value. So you can basically create a proportionality that Q will be proportional to R squared. Do you guys understand this? Now, all you need to basically do is that you can write Q, for example, A will be equal to R A square, and then you can take the ratio like this. So the charge of sphere B is going to be RB whole square. This is how you can create a ratio of the quantities that are changing within some common values. Now, what I need to find is I obviously need to find the charge on. I need to find the additional charge on this. So let's look at that. So this one, if I want to find QB, so it will be QA times RB square over RA square. Now obviously, the charge is Q on this. So that means it will be Q. RB is 52 whole square and it's being divided 26 whole square like this. That means that I just need to take this ratio, 52 whole square divided by 26 whole square, and it should give me 4 times the charge. Now, the question is a trick question, and it says you got to find the additional charge. So obviously, the first one had Q, so additional charge is not going to be 4Q. In fact, it's going to be 4Q minus Q because that would be the extra charge if you put it in. That's when the electrical breakdown is going to occur. So the answer is 3Q, not 4Q. Get it, kids?
Yes, sir.
Whose I didn't get your work? Why? Okay. Now I'm going to go to the next and let's talk about. All right. So what is meant by electric field strength? Now, this time it is a 2-mark definition. Okay. Now, whenever you will have a 2-mark definition, you guys need to include the keywords as well, because obviously that would be required. All right. So, if I were you, I would basically write that it is the force per unit. Now, this keyword that I mentioned before as well is a unit positive charge. Now, obviously, the definition is as simple as force per unit charge, but when you add this keyword, you're going to get one extra mark. However, just make it your habit to always write positive so that even if they're giving it, they're giving this like for 2 marks, you still get two, even if they've given 1 mark. All right, so just make it a habit so you don't forget. Anyway, now 2 point charges A and B are situated at a distance 15 centimeter apart in a vacuum as illustrated. Right? Now point P lies on the same line joining the charges and distance x. Fair enough. The variation of distance x electric field stent E at point P is shown. So first of all, they're saying by reference to the direction of electric field, state and explain whether the charges A and B have same or opposite signs. So let's suppose if A was positive, it would have the field strength going outward because the field always goes out of positive. So let's say with electric field strength is a vector quantity. That means if I take right side as positive, as shown on the graph as well, then the other line shows that it is negative, which means that the field from B should be out as well. That means that the left side should be negative and they must be both charges must be positive charge. Do you guys understand this?
So can you repeat why you said B should be negative?
If you see the graph, right, the
Yes,
section here is all positive, right?
yes,
That means because electric field strength is a vector quantity, that means that the field must be coming out of the charge, right? So I
yes.
took right side as positive. That's why I'm saying the field should be towards the right. Okay. Now, if you see when it reaches near chart B, the graph becomes negative. That means that actually the field should be in the opposite direction now. Understood?
Oh, okay, okay. Thank you.
That is why I know that these two charges are of same sign. If you had taken them as a negative charge, both of them is negative, then it would also work. Like, let me show you that. If A was a negative charge, the field would go inside. So if I take this as positive, then a negative charge here would also mean the field will go in this side because the field is opposite. That means this should be negative then. Understood? So it doesn't matter like that. So what I want you to basically write here for 2 marks, if I were you, okay, I would say number one, that electric field strength is a vector quantity. Now, because as you see, it says by reference to the direction of electric field. We're also talking about this already. So I'll say the direction of field for both charges is opposite, right? Hence, they must be like charges because that's the property of like charges. They have the same type of field. When you look at a single line, they will always appear opposite to each other. Understood, kids?
Yes, sir.
Right. So they have the same sign. Now it says state why, although the charge A is a point charge, the electric field strength between 3 to 7 centimeter does not obey an inverse square law. Now, the thing is that if you look at the diagram, it basically crosses this, whereas inverse square law means it should be like, it should keep on decreasing as the distance increases. The thing is, it would not obey inverse square law because you're not only looking at A, but every single point on this line is also being influenced by B. So it's not an isolated chart. Do you guys understand this? So if I were you, I would say that charge A is not isolated, so the field is influenced by charge B as well, I guess. Right. All right. Now, the next one says use figure 5.2 to determine the magnitude of charge A and magnitude of charge B. Well, that's pretty easy considering we have the graph here, right? So what I'm going to do is you can basically, this is the field, the net field graph. So it's pretty common that you're going to get something like this, right? So as you can see at this spot, both the electric field strengths are zero, right, kids? Which means that at this spot, the electric field strength A and the electric field strength of B must be equal because that is the null point, right? Is that clear, kids?
Yes, sir.
So I'm gonna say I'm gonna say at 10 centimeter, electric field strength of A should be equal to electric field strength of B. Now I'm gonna apply the equations. K cube A over R A square equals to K cube B over R B square. So this is the formula. K and K will cancel out. Now we got to find the ratio of charge. So Q A over Q B should be R A square over R B square. Now how do we find R? We're gonna go from this point and we're gonna see what exactly is the value from here to the point right here. Now it's pretty simple. This is going to be 2.4, 2.8, and that's 10. So this distance is going to be, I think, 10 minus 2.8. So you got 7.2 centimeter here. And for the other chart, I'm going to do the same thing. It is basically somewhere here. I'm not sure what that is. But this will be, I think, 12 point. Wait a second. This one is 12.4, 12.8, and 13.2, something like that. And that's 13.6. Okay, let me think about it. It should be somewhere in the middle of that, which is from 12.8. It should be about 13, I think. I think so. Maybe. What kind of graph is this? Oh, you can't do this. They've given 15 centimeter as well. And that's bad. So from zero, if you consider the zero and you consider this point as the null point, I think so the null point is from this is x, so it is at 10 centimeter. That means the distance from here to here is 10 centimeter. And then from distance to here is 5 centimeter because total is 15. Because this is not the full graph they've shown. Anyway, so we got 10 and we got 5 for this is RA and this is RB. So let's put it the equation. So 10 squared divided by 5 squared. So let's find it out. So it should be 4.0. Is it clear, kids?
Yes, sir.
Furkan, I want to know why haven't you done the work? Yes, please. Now I'm going to go to the next. Now again, now this time they're asking about electric potential. So the first part will be when you write it is the work done per unit charge. Now this is 1 mark. The second mark is when you start writing that you're writing that to bring this charge from a point at infinity. All right, so this is the complete definition that you're going to write for 2 marks. Now, this is a parallel plate system. In a parallel plate system, you guys need to understand that electric field strength is constant. And keeping that concept in mind, I'm going to go forward. The distance between the plates is B, and the potential difference across the plates are V naught minus 0, which means V naught. Now, what I'm going to do is, Furkan, just send it to me as soon as possible. Okay. So, yeah. Now they're saying draw the line. I told you before as well. Basically, here you have at distance 0, at x equals to 0, you have the potential V naught. So we're going to start the graph from V naught. And then we're gonna move from here till here. So at x equals to d, that's when the potential is 0. So that means at d you have the potential 0. And a constant electric field strength basically means that it should give you a straight line like this. Understood, kids?
Yes,
The
sir.
reason why this has a negative gradient and it is a straight line because number one, in uniform field, E is constant, so the gradient will be constant. And number two, E is basically the negative potential gradient. So whenever you have a potential graph, so E will always be the negative gradient of that. That's why it has to be like this. Now, the next part, they have given you two spheres, both positives, M and N, and they have given you Y and distance D, which is A. And they want you to draw the potential of this. Now, keeping that in mind, I would want to know what kind of charge. They both have the same charge, which means that their potential and the radius is the same as well, which means the potential is given by KQ over R. Now, potential is a scalar quantity, and obviously, if it's a positive charge, so potential at the surface of these is going to be positive KQ over R as Q is positive. Potential at the surface of this one will also be KQ over R, and it will be positive because it is just a positive charge. Now, what you're going to do is you will have to then draw this graph. The radius of the first one is this. So I'm going to just put it anywhere, wherever you feel like. You can start from this point. And then this point is obviously D minus R, right? So you can start from D minus R and put it at the same spot like this. Now, naturally, it's gonna, the way I've taught you this, I'm going to draw the individual graphs just to show you what it means. Well, it's not necessary to do that. For R, the potential within the sphere stays constant because it's a metal sphere. And then it starts to decrease like this. And for the other one, it's going to be the same. It will be constant from the center, and then it will decrease this. The net graph they're asking for, so we're going to add all the potential at each individual distance, and it is going to give you a line like this. So you can erase the other lines, and it should look like this. Is that clear, kids? It's always look like this. Okay. Right. Yes. Asma, Malik, Shazib, Musa, Gurban, everything is clear. Very good.
Yes.
Then, my kids, we're going to go to the next. Again, it's the same electric field definition. It's 2 mark, 1 mark for writing force per unit charge. And then the other mark, if you write positive. This is basically the second mark, so please remember that. Anyway, so this time, I think this is the similar question. I don't know why it's repeated. It was the same question actually. For some reason, it got repeated. Anyway, now we're going to move towards this. Electric potential at this point, you already know. It is work done per unit charge. And then the second mark is when you write to bring it from infinite, right? So this is the second one. The relationship of electric field strength and electric field strength. I have basically told you that just now that basically electric field strength is the negative potential gradient, right? So I think if you just write this in this question, it would be pretty good. Okay. All right. So I hope you guys understand this. Then we're gonna go to the next. This is again a parallel plate system. Yes, Furkan. Yes, Furkan. Furkan, you have something to say? Okay. All right. So now I just wanna like you guys know now the parallel plate system means that the field has to be constant, the field strength. So it is Earth, you have the distance d between them and the potential difference as well. So it says helium nucleus situated between the plates and a distance x from plate A. Obviously, helium nucleus will carry positive charge, as you guys know. And initially, helium nucleus is at rest at x equals to 0. Okay. The helium nucleus is free to move between the plates. By considering energy changes of helium nucleus, explain why the speed at which reaches plate B is independent of the separation of the plates. Right. Now, this is a kind of a interesting question. First of all, we should understand that what kind of energy the charge is going to have initially. Obviously, it must have electrical potential energy because it will be at a certain potential initially. And then this electrical potential energy loss will be equal to the gain in kinetic energy. We'll start, right? All right, kids, everything is clear here.
Yes, sir.
Now, the question is that we need to prove that the speed at which it reaches the plate is independent of the separation. Okay. So, electrical potential we know is change in electrical potential times charge, and this is half mv squared. As you can see, that actually in this question, in this formula, there is no separation given. So that means V is not dependent on D, sorry, on separation. They're not given to you. Right? There's nothing to do with it. V has nothing to do with the whole formula. That's why. Right. Then you have the helium nucleus moves from plate A towards B. A to B, okay, like this. Very well. So that means it says calculate the speed nucleus. We already written the formula, which is very good. So we're going to carry on with the same thing. First of all, let's understand helium nucleus. Helium is given by 4U, which means its mass is equal to 4U and its charge is going to be equal to 2E. The potential difference between plates is 0 minus 75. So you always take the larger value and then subtract the smaller value in scalars because potential is a scalar quantity. We're going to have 75 as the potential difference. And the distance between them is 1.2. Well, I don't think we need that. So 75, the charge on this is 2 times 1.6 into 10 raised to minus 19. Half the mass will be 4 times 1.66 times 10 raised to minus 27. And we got to find the speed like that. All right, kids? Okay. Let me check out. But there is one issue here as well that I've just noticed. That it doesn't say from the start, it says calculate the speed after it has moved the distance of this. Interesting. So that means we need to find the potential at this first. And that's pretty bad. We can't use 75 then. Okay, I'll do this. So if 1.2 centimeter has 75 volts of potential difference, then the distance x they're given is 0.40. So what will be the potential difference between this? I'm going to cross multiply this. 75 times 0.4 divided by 1.2. Let's find it out first. Hassan Bajwa, why are you that late, my friend? So this should be only 25 volts. So the difference between this will be 25 volts. That's what you're going to show. Okay, and what about the worksheets that you haven't submitted? Now I think we will be able to do this. Okay, let's try that. 25 times 2 times 1.6 times 10 raised to the power minus 19. And then multiply by 2 divided by 4 and divided by 1.66 times 10 raised to the power minus 27. And then we have to take under root. So the answer, oh my goodness, that is a huge answer actually, which is 4.9 into 10 raised to power 4 meters per second. So, well, that doesn't make sense. Let me check the answer for this. I about it. Okay, so this is 4/1 October 18. 1 second, let me just confirm the answer. Where is that app? I've forgotten about it. So papers, wait a second. levels. They changed the app actually to this. Was 4-1 October, November 18th, winter 4-1, 2018. Winter 4-1. 4-1. Okay. Oh yeah. We got this right answer, which is very good. So everything is fine now. We can continue. Everything is clear, kids. Should I go forward, please?
Yes, sir.
All right. So this would be the answer then. And now let's. So what is meant by electric potential? Now you guys already know what is the relationship. I think this question, like, oh no, it's not. It's a new one actually. So you have to write electric potential. Electric field strength is negative. Potential gradient. Anyway, so both charges in this case are positive, as you guys see. The charge on Q is A larger than the charge on B. So this has a smaller charge, right? And distance B, blah blah blah, and you gotta create the potential now. Again, the same thing. This time, obviously, the one that has larger charge because potential is KQ over R. So the greater the charge, the greater the potential it will have. So we're going to start with the higher point of this. Let's start from here. So within the space, it is constant, and then we're going to start from this point. And I'm going to make the individual graph first, just for my own understanding. And then for B, its potential should be smaller. So you can basically start from any point less than the first potential. Okay, you can start from there. I think so. Right. And then just do it like this. And then the net graph of this is going to go like this actually. We can erase this and it should look like this. Is it clear, kids? Right. Now, yeah, pretty good. Now, the thing is, oh, this was 4 marks, only this. That is pretty insane. Nothing else actually. It is pretty good actually. 3-4 marks if you remember the graph actually. Right. Now going to the next one. Again, the same thing he has asked. And I think this one's a repeated question. Okay, this one's. So state an expression for electric field strength at a distance r from point Q in a vacuum. State any symbol you use. So now, just remember, I have repeatedly, like I use the equation E equals to KQ over R square all the time. But I told you K is not a real constant, it is a derived form of the real constant. And that is the real formula is 1 upon 4 pi epsilon times Q over R square. So whenever he's going to ask you to explain some symbols or whatever, you use the real formula, okay? So when I say E equals to 1 upon 4 pi epsilon times Q over R, like that, R squared. Now it says any other symbols that you're going to use, just explain, because he has already told you what is R and Q, so you don't need to explain that. You just need to explain E naught. And you're going to say it is the permittivity of the free space. This is what you're going to write. Tickets. Everything's clear? Right. Yes, Asma, Malik, Shazib, Musa, Furqan, Hassan. What about you? Right. Okay, now going to the next. They've given you the graph of electric field strength this time with centimeters here. And they say explain whether the charges are same or opposite sign. Now, this is the similar kind of question. Think about it this way. Okay. If you look at the graph, you might see that electric field strength is positive all the time. It's never negative. The only way this is possible is because if let's suppose you have a positive charge, you have a negative charge. Positive charge field goes out. So you're gonna take, let's suppose you take this direction. Oh my goodness. Let's suppose you take this direction as positive and you take this direction negative. So the negative charge field also goes into it. That basically means at this point it will also be positive. So the field direction is the same and electric field strength is a vector quantity. That means that it is showing you the whole thing in the positive region. The other thing is that you can check is if these were for same charges, obviously they would have a null point in the middle. And null point means at this point electric field strength should be zero. But in this graph, no matter where you see, electric field strength is never zero, which means it is a graph between two opposite charges. Is that clear, kids? Or unlike charges? Yeah, so this is what you need to keep in mind. And now let's write it down. This. So this said state and explain. So first I'm going to state their opposite signs. And either I'm going to say that basically they don't form a null point. So E is never zero. One is this explanation. The other one is that the direction of P is always in same direction or same, yeah, always in same direction in a straight line between them. So you can write this or you can write three, but it's okay. Whatever you want to write, so all right. Okay. Now, keeping that in mind, let's go to the next and say have the same or different magnitudes. Now, as you can see, it's a pretty symmetrical graph. So that means that they must have the same magnitude as well. If the magnitudes are different, then the graphs sort of form like they get skewed from one end. If it's a symmetrical graph that you see right now, like this, then it basically means that they must have the same magnitude. Now the problem is how are we going to write that? We're going to say it's a symmetrical graph that forms the midpoint at the center of charges So magnitude must be same or anything of that sort. Okay. Now it says electron is situated at point B. Without calculation, state whether the variation in magnitude of acceleration of electron as it moves from 3 to 7. So if it's moved from 3 to 7, obviously the 3 is this point. At this point, the electric field strength is quite high. And as it moves from 7, it basically reaches, I think at 7, it reaches the same spot, right? Same, almost the same spot. No, I think it is the same spot. Probably. All right, maybe not. But the idea is that as it's going to move from this end to this end, you can realize that the electric field strength is going to reduce till the point which is 5 centimeter, and then the electric field strength increases again. Now, electric field strength itself is basically force per unit charge. Force is ma over q. So if I compare A with E, so it's going to be EQ over M. Charge is the same, mass is the same. So A is directly proportional to E. That means greater the electric field strength, the greater the acceleration. So we're going to say that from 3 to 5, it is going to reduce its acceleration, E reduces, and then it's going to increase its acceleration as it goes further. Is that clear, kids?
Yes, sir.
So it is of 4 marks actually. Okay, that's pretty. So that means we have to give the equation as well. We're going to say acceleration is proportional electric field strength. This should be your first mark. If you don't want to write it, you can give the formula AQ over M like that, right? And say A is proportional. That might work as well. Then the next point you're gonna write is that from 3 centimeter to 5 centimeter, acceleration decreases as E decreases. And from the third point will be at 5 centimeter, acceleration will be minimum, but not zero, because electric field strength is not zero. Number 4, from 5 centimeter to 7 centimeter, I'm going to say acceleration increases as E increases. So that would give you a full 4 mark credit for this question. Okay, kids. Please make any corrections that are necessary to this. It would be very, very nice then. All right. Now, we're just short of time, so we'll solve the last question. This. You have 2 spheres, the distance x, the distance between them from center to center is 4. And they have given you a graph of potential this time. Very good. Now, they say experience whether 2 spheres have same or opposite sign. Potential is a vector scalar quantity. So obviously, if the charge is positive, then the potential will be positive. If the charge is negative, the potential will be negative. So this is the graph for charge 1. So charge 1 has to be positive because the value of potential is positive. Here the value is also positive, so the other charge should be positive as well. Get it, kids? The other way of looking at that is that if you take the gradient at this spot, that is a flat line between the electric field strength and 0, and that means this is the null point that is forming. So you can write both the points if you want to do. Right? If I were you, I would make my life much easier. I would say that potential for both charges is positive, so they must have same sign, right? So I'm gonna make it pretty simple here. Okay. Then the next part is a positively charged particle at rest on square A. The particle moves freely from A to B, and then they're saying describe qualitatively if the if any with the distance like the speed of particle as it is. Now the thing is that at this potential, as you can see, the gradient is there, so there must be some acceleration. And then as it's gonna change the potential, you see, the potential is decreasing. Now, if the potential decreases, that means the potential energy is decreasing. Where is it going to? It's going to convert to kinetic energy. That means till this point, which is actually the I think that's 26. Till 26, you will have the velocity will increase to its highest value. And then afterwards, as you can see, the velocity now potential increases a bit. That means some kinetic energy will be lost to potential energy again, right? So that means the speed is going to decrease, but it's not going to be as low as when it was at this value, right? So it's less potential increase. I'm going to write the same thing. They're saying moving from 12 to 25. What is 25 at? Okay, this point, right? 25. So obviously, I would say that speed would increases, and you just need to. I don't know if I'm not sure if you. This just said describe, and in my opinion, if they're saying you just need to describe, so probably you don't need to write a lot of explanation. This just write increases, decreases, whatever. So and passes through this. So at this point, when it is passing from this. So obviously at 26, like I said, that is the lowest potential, which is highest kinetic energy. So let's say maximum speed. And then from 27 to 31, obviously speed will decrease, right? So, but you can write that it's gonna, because it's less, so you can include the acceleration as well at the some rate. So at lower rate, that would be at higher rate. That better. You can describe that as well. And when it reaches 35, obviously 32. At 32 exactly, it is the gradient is still like this, which means there is electric field strength happening and there will be acceleration. So speed will continue. Speed will continue to decrease. Is that clear? If it's any questions there?
No, sir.
Now, finally, they say the chart has this and mass is just calculate the speed of particle, the maximum speed. So obviously, you're going to find the potential at the max lowest point. The potential right here is somewhat like I'm not sure what that is. I think it is. If this is 1.2, 1.4, this is 1.5. So this will be 14.2, 14.4. So it's going to be 1.43. And at this spot, the potential is this 2.1, so 2.2, 2.12, 2.14, 2.14. So 2.14, well, that's fine. And then you can subtract it, this 10 raised to 4 as well. So the change in potential is going to be 2.14 into 10 raised to 4 minus 1.43 times 10 raised to 4. That will give you the change in potential. And then all you need to do is you need to multiply the charge, the change in potential times charge, and do half mv squared. You have the mass given, you can find this speed. Let me state it. All right, so I have another class just now. So I will inshallah then